Hello students, welcome to EPG Pathshala. I am Dr. Ayushi Paliwal from University of Delhi. Today we are going to discuss the module Quantum Confinement of Electrons in Semiconductor Nanostructures under the paper Nanoscience and Nanotechnology First. So students, let us see what we are going to learn in this module. First, the importance of particle in a box system will be discussed. Second, the wave functions and the energies of a particle in a one-dimensional system will be derived. Third, we will derive the wave functions and energies of a particle in two-dimensional system. Lastly, we will derive the wave functions and energies in three-dimensional system. Particle in and one-dimensional system. One-dimensional system or 1D system is the simplest form of the particle in a box model. In this model, the particle can move only in backward and forward directions along a straight line and is surrounded by impenetrable barriers at either end. The walls of a 1D box can be visualized as the regions of space which have infinitely large potential energy. On the contrary, a constant zero potential energy is assumed to be present within the box. This implies that the particle is free to move within the box and no forces act upon in this region. Further, owing to infinitely large potential energy at the walls, very large forces are applied on the particles by the walls of the box. These forces repel the particle when it touches the walls of the box. Thus, the particle cannot escape the potential well. Potential energy in the case of 1D box can be calculated as Vx equal to 0 when x is varying from 0 to a and is infinite elsewhere. So the Schrödinger equation in this region is minus h cut square by 2m multiplied by d square by dx square plus Vx, this whole multiplied by psi equal to E psi, with the boundary conditions shown in this figure. So this figure schematically shows a one-dimensional particle in a box system. The barriers outside the box have infinitely large potential, whereas the interior of the box has a constant zero potential. So the solution to the Schrödinger equation in the region of interest V equal to 0 is given by d square psi by dx square equal to minus 2me by h cut square psi, whereupon letting k square equal to 2me by h cut square yields the following second order differential equation, that is d square psi by dx square plus k square psi equal to 0. So the general solution to this is a linear combination of plane waves, that is psi x equal to a exponential iota kx plus b exponential minus iota kx, where a and b are constant coefficients to be determined, must go to 0 at the origin. That is psi 0 equal to 0. Therefore, we get psi 0 equal to a plus b equal to 0, or b equal to minus a. So this gives the complete wave function, that is psi x equal to a multiplied by e to the power iota kx minus e to the power minus iota kx, which can be rewritten using the Euler's relation, that is psi x equal to 2ia sine kx. So now, if we apply the second boundary condition, we get psi a to be equal to 0, that is psi a equal to 2ia sine of ka equal to 0. So at this point, in order to obtain a solution, we have either a equal to 0 or ka equal to n pi, with n as the integer. Now a equal to 0 just means that the wave function is 0, which is not possible. So k values are restricted to k equal to n pi by a, where n is a normalization constant to be determined. So this is the general form of wave function for a particle in a one-dimensional box. So students, let us start with a basic introduction about the module. Quantum mechanics describes the particles in a box model as a particle which is or which can freely move within a small space surrounded by impenetrable barriers. So students, this model is termed as infinite potential well, or we can say infinite square well. It is mainly due to its structure. This model is specifically employed as in theoretical investigations to demonstrate the difference between the classical and the quantum systems. So in the case of classical system, a ball which is entrapped within a large box is free to move inside the box at any speed and has equal probability of being found at any point inside the box. Nanoscale dimensions, quantum confinement effects assumes importance. So as a result, the particle is no longer too free to move anywhere within the box, but can only occupy specific energy levels. Additionally, it cannot have zero energy at any moment, implying that the particle is never at rest. Furthermore, depending upon the energy levels, the probability of finding the particle at certain positions is more than at other places. Thus, the particles may not be detectable at some specific positions. So these positions, which have zero probability of particle occupation are termed as special nodes. Let us now discuss about the normalization. The probabilistic interpretation of wave functions means that they must be normalized. That is, the particle must be located somewhere within the box with unit probability. That is, the probability is equal to 1 equal to integral 0 to infinity psi x psi star x dx equal to integral 0 to infinity n square sine square n pi x by a dx. We therefore solve the above integral to find the normalization constant n by invoking the trigonometric identity sine square m is equal to 1 by 2 multiplied by 1 minus cos 2n. So this gives 1 is equal to n square by 2 multiplied by integral or the limits 0 to infinity x minus 0 to a basically, because we are considering particle in a box, integral 0 to a cos 2 n pi x by a dx. So this is equal to n square by 2a. So now if we'll calculate the value or the expression for n, so n will be equal to root of 2 by a. So this figure shows the first three wave functions along with their probability densities. So as you can see over here, we have psi 1 corresponding to n equal to 1 and the probability density is psi 1 square, psi 2 corresponding to n equal to 2, psi 2 modulus square, psi 3 corresponding to n equal to 3 and the corresponding energy, the corresponding probability density is psi 3 modulus square, where n equal to 1, 2, 3 and so on. Now note that the quantum number n is never 0, as this would violate the Heisenberg uncertainty principle. So students, this figure shows the first 5 energy levels of the particle in a box along with their corresponding quantum numbers. Note the absence of degeneracies, that is multiple levels having the same energy in the one-dimensional box energy levels. Apparently, the states are more closely spaced together at lower energies but become more distant as the n increases. System. So the wave functions and energies have x and y dependencies. Additionally, an important consequence of working in higher dimension is increased likelihood of finding degeneracies, implying that there will be increased propensity for finding states that have the same energy. This stems from built-in symmetries of the system. So the Schrödinger equation in this system can be written as minus h cut square by 2m del square plus v as a function of psi x and y multiplied by psi xy equal to e psi xy. So in two dimension, the Laplacian takes the form del square equal to del square by del x square plus del square by del y square. So putting the value of del square in the equation, it becomes minus h cut square by 2m multiplied by del square by del x square plus del square by del y square plus vxy multiplied by psi xy equal to E psi xy. So we assume the potentials and the boundary conditions as shown in this figure. Namely, we have a symmetric box with the dimension A along each axis and with a potential that is 0 inside the box but is infinite outside the box. So the particle is therefore confined to the interior of the box. Y equal to 0 for 0 less than equal to y less than equal to a. Psi x0 equal to 0 for 0 less than equal to x less than equal to a. And psi xa equal to 0 for 0 less than equal to x less than equal to a. Divided by psi xy equal to E psi xy. So for simplicity, let us assume a separable solution of the form that is psi xy equal to psi x multiplied by psi y, which is basically the product of two independent wave functions, each with its own x or y dependence. Simplifies to a great extent. So now introducing psi equal to psi x psi y in the Schrodinger equation and dividing both the sides by psi x psi y, it yields 1 by psi x multiplied by minus h cut square by 2m d square psi by dx square plus 1 by psi y multiplied by minus h cut square by 2m multiplied by d square psi y by dy square equal to E. So now this relation remains valid for all the values of x and y. Consequently, each term on the left hand side must equals a constant. These constants turns out to be the energy contributions from x and y. So we can write E equal to Ex plus Ey. So now we can separate this equation into the two smaller ones where there is only x dependence and the y dependence. Square psi y by dy square equal to Ey psi y. So these are the two-dimensional particles in a box problems, which demonstrates how assuming a separable solution greatly simplifies the original two-dimensional problem. Now, both these one-dimensional problems can be solved as shown above. So the wave functions for this kind of system are, so when everything is put together, the total wave function for the particle in two-dimensional square box is psi xy equal to 2 by a sine of nx pi x by a multiplied by sine of ny pi y by a, where nx and ny are the independent integers. So this figure shows the first few wave functions of a particle in a two-dimensional box and the associated probability densities are also shown in this figure. So the obtained independently normalized wave functions are psi x equal to root of 2 by a, sine of nx pi x by a, psi y equal to root of 2 by a, sine of ny pi y by a. So with the corresponding energies as Ex equal to nx square h square by 8ma square and Ey is ny square h square by 8ma square. So in both the cases, nx and ny are their integers reflecting the quantization of the particle. Can be 1, 2, 3, etc. So the figure over here illustrates the energies of the particle in a two-dimensional box. Since the box is symmetric, so there exist a number of degeneracies where different states ends up having the same energy. So as seen from this figure, the state characterized by a quantum numbers nx equal to 1, ny equal to 2 possesses the same energy as the state with the quantum number nx equal to 2, ny equal to 1. Note that these degeneracies can be lifted by making the box asymmetric by 8m multiplied by nx square by a square plus ny square by b square. Particle in a three-dimensional box. So here also there are degeneracies. Let us now consider the particle trapped inside a three-dimensional box having equal lengths on all the sides, that is a cube. So the relevant potential and boundary conditions are shown in this figure, where a box with a length A on all the three sides and a potential of 0, infinity and inside, and it is outside, it is infinite. So the boundary conditions are systematically shown in this figure. The boundary conditions and the procedure explained for the two-dimensional and one-dimensional systems can be applied in this case in a similar manner to obtain the resulting particle wave functions and energies as psi xyz equal to 2 by a to the power 3 by 2 multiplied by sine of nx pi x by a multiplied by sine of ny pi y by a multiplied by sine of nz pi z by a, and E equal to h square by 8ma square multiplied by nx square plus ny square plus nz square, while nx, ny and nz can vary from 1, 2, 3, etc., which are the quantum numbers reflecting the confinement of the particle. So this figure illustrates the first few energies of the particle in a three-dimensional box. Again, because of the system's high degree of symmetry, there are significant degeneracy with multiple states having the same energy. So students, let us now summarize what we have learned in this module. First, we discussed about how important is to discuss the particle in a box system. Secondly, we derived the wave functions and the energies of a particle in one-dimensional system. Thirdly, we discussed about the wave functions and energies of a particle in a two-dimensional system. Lastly, we also derived the wave function and the energies of a particle in a three-dimensional system. Thank you.